The Rotax 912 has been the definitive benchmark in the 80 to 100 horsepower aircraft engine segment for over 30 years. While some engines beat it on cost, others on fuel consumption or power to weight ratio, no single engine outperforms it across all metrics, and in my opinion, its reliability in this segment is unmatched. At first glance, the 912 might not appear particularly unique from a design perspective, but looks can be deceiving. We're going to dive deep into the design of the Rotax 912, including explaining its more controversial features like the propeller speed reduction unit and liquid cooling system. Development began in 1984, with the 80 horsepower 912A receiving type certification in 1989 with a 600-hour TBO. The 100 horsepower 912S followed in 1998 with a 1,200-hour TBO. As confidence in the engine's durability grew, TBOs first increased to 1,500 hours, then 2,000 hours by 2010 for both variants. Today's non-certified versions are designated the 912UL, the 80 horsepower, and the 100 horsepower variant is the 912ULS. The fuel-injected 912IS launched in 2014. While development of the turbocharged 914 began in 1990 and evolved into the 915IS and the 916IS, this video focuses on the 100 horsepower 912 variants. By 2014, Rotax had already produced 50,000 of its 900 series engines. The 912 powers over 500 different aircraft types, including popular fixed-wing planes like the Sling II, Kitfox, RV-12, CH-701 and Tecnam P-92. This widespread adoption happened for very good reason, as we're about to see. I won't read the whole spec sheet like a robot, I'll show it on screen, but the highlights of the 912 is it's a liquid-cooled, well, sort of, we'll get to that, 4-cylinder boxer, 4-stroke engine displacing 1.35 liters, producing 100 horsepower at 5,800 RPM. At that RPM, a propeller speed reduction unit is essential. It runs on both MoGas, or automotive petrol, and avgas. The Rotax is frequently compared to the Continental O-200, which was designed in the 1940s, which also produces 100 horsepower. While I don't think it's entirely fair to compare the 1940s O-200 with the 1980s Rotax, I usually get plenty of comments from viewers insisting they'd rather have the O-200. So, your wish is my command. The Continental is a proven workhorse, and that it's been manufactured for over 70 years speaks volumes. However, it doesn't compete with the Rotax in most metrics, which is understandable given the decades of technological advancement that has happened since. The Rotax delivers more than double the specific power, better power to weight ratio and specific fuel consumption, all while being cheaper. The main argument for the O-200 is reliability, and it is reliable. But the Rotax is at least as reliable, with some statistics suggesting it is even more so. If you think that's a bold claim, check out the links in the description below. No need to take my word for it. A more modern competitor is the UL Power UL260i, an air-cooled direct drive like the O-200 but with smaller displacement and fuel injection. The 260iS version competes even better, weighing the same as the I variant but producing 107 horsepower. Another 100 horsepower option is the Aero Momentum AM13, based on Suzuki's G13 engine which powered cars like the pre-2000 third generation Jimny. It's a liquid-cooled inline-4 automotive engine built from brand new components. Still, it blows the Rotax out of the water in one area: cost. There's also the MW Fly Spirit 100, a liquid-cooled direct drive Boxer 4 that competes fairly well, though it's somewhat heavier. There's a few more less popular engines in the 90 to 110 horsepower class, but I'd really like to focus on the Rotax 912. So let's dive deeper into its design. The 912 has the standard boxer layout, opposed pistons with connecting rods on separate 180-degree offset crank pins. This creates the familiar movement where pistons move outward together, then inward together in pairs. The fire interval is an even 180 degrees as expected. Despite the connecting rods not being fully aligned, the Boxer 4 achieves perfect primary balance. However, this misalignment creates a slight rocking couple due to secondary imbalance forces. I won't cover mechanical balance in detail here as I want to get to the controversial features. I'll link a previous video where I've thoroughly covered Boxer 4 balance if you're interested. It's not critical info anyway, as the 912 runs quite smoothly thanks to its relatively lightweight reciprocating components, and based on personal experience, very little 912 vibration transmits through the engine mount rubbers to the cockpit. 3 criticisms usually come from those unfamiliar with Rotax engines, but still willing to share their opinions. First, it's liquid cooled. If it loses coolant, the engine seizes. Sure, if enemy fire hits your coolant system, it'll drain and seize. Oh, wait, this isn't World War II, nobody is shooting at you. Being serious for a moment, yes, coolant can leak. But unlike your car's neglected coolant system, aircraft systems get regular attention. While Rotax doesn't specify coolant change intervals, most certified A&Ps replace coolant every 1 or 2 years. And why wouldn't you? It's easy and cheap. Cooling components get inspected every 100 hours or annually, with rubber hoses replaced every 5 years. Follow Rotax recommendations and the cooling system won't give you trouble. In my several hundred hours behind Rotax engines, I've never even needed to top up coolant. The certified Rotax mechanics I have contact with, after decades of working on these engines, have never witnessed a case of in-flight coolant loss. Not a single case. The cooling system as a major drawback compared to air-cooled engines is a myth propagated by those who don't know any better. Another criticism I often hear, especially when comparing Rotax power-to-weight ratio to air-cooled engines is, quote, "But you still have to add the weight of the coolant and cooling system," unquote. As if it's a 30 kilogram penalty. The 912 holds just 1.5 liters of coolant in total. I shouldn't need to explain how little that weighs. That is about a third of the coolant your car takes. Here's why. The Rotax isn't truly liquid cooled. It's hybrid cooled. Only its cylinder heads are liquid cooled. Notice the cooling fins on the cylinders themselves? They're air cooled. This requires much less coolant and a radiator about a quarter to a third the size of that on your car. Yes, it adds weight, but the 912 remains lightweight overall, and my earlier comparisons included typical cooling system weights. There is a downside though. With air-cooled cylinders, you still need proper airflow through the cowl, or you'll have issues with high temps. Both our previous 912 powered aircraft had initial cooling issues, but that was solved with basic airflow knowledge and some trial and error. Quite ironically, it's the air-cooled portion that's prone to issues, not the liquid-cooled part. The second complaint by those who don't really know is it runs high RPM, 5,800, can't be reliable. But it isn't just RPM that affects engine wear and longevity. In fact, a more important factor is mean piston speed, which is affected by both engine RPM and stroke length. A shorter stroke length means lower piston speeds for the same RPM. Both the 912 ULS and O-200 are over-square engines with a bore larger than its stroke, typical for boxers that can't be excessively wide. But the Rotax has a much shorter stroke, resulting in quite low piston speeds for its RPM. Here's the numbers. The O-200 at 2,750 RPM with a 98.4 mm stroke has a mean piston speed of 9 meters per second. The 912 at 5,800 RPM with a 61 mm stroke achieves a mean piston speed of 11.8 meters per second. Despite running more than double the RPM, the Rotax's piston speed is only 30% higher. Even so, that 30% higher doesn't necessarily mean it will have a 30% shorter life, as there are other factors at play too, and Rotax 912s usually easily reach its 2000 hour TBO, with many flying on condition beyond that. So, statistically speaking, the high RPM problem argument holds no water. Of course, at a max of 5800 RPM, it does need a propeller speed reduction unit, since no decent sized propeller can spin that fast. And this brings us to the third complaint from the unfamiliar. I refuse to fly behind a Rotax because it has a gearbox. If I had a dime for every time I heard this, I'd be, well, not rich, but I'd have a piggy bank full of change. Let's assume these people aren't hypocrites and they also refuse to fly on helicopters and turboprop-powered airplanes, as both use gearboxes, and address the concern. Maybe let's also not tell them that many turbofans in development earmarked for modern airliners are geared turbofans. Yes, the gearbox adds a failure point. Yes, some custom gearboxes on auto-converted engines have created problems and caused failures. But the Rotax isn't auto-converted, and its well-designed and robust gearbox units rarely give issues when properly maintained. Maintenance includes 100-hour friction torque checks, 600-hour overload clutch inspections, and 1000-hour gear wear inspections by qualified personnel. These gearboxes rarely fail completely. Ask any Rotax certified mechanic. Don't ask A&Ps unfamiliar with them. Another opinion frequently aired is that gearboxes add friction and weight. It's true, it does both, but those friction losses and additional weight are already accounted for in the final specs, and the Rotax still comes out superior. The advantages outweigh the drawbacks, and here's how. Direct drive engines hit a hard RPM limit due to propeller tip speed limits about Mach 0.8 before efficiency plummets. This caps engine speed around 2700 RPM. To make power at low RPM requires massive torque, meaning massive displacement. It's in the equation to calculate horsepower. You need high RPM or high torque to produce high horsepower. If RPM is fixed due to a direct drive propeller, it only has displacement as a variable to achieve a given horsepower number. In addition, with a gearbox, the designers can let the engine run at an efficient cruise RPM, say 5200 in the case of the 912, while slowing the propeller to 2200 RPM with the 2.43 to 1 speed reduction. This enables larger propellers, and actuator disk theory shows slower spinning propellers need less engine power to create the same thrust as a faster spinning propeller. So, since the 912 has a slower spinning propeller, it is inherently more efficient. Higher RPM engines often get criticized for having low torque, but that argument misses the point entirely. Yes, the Rotax has less torque than any direct drive 100 horsepower engine like the O-200 at the crankshaft. It has to, since power equals torque times RPM. Same horsepower, higher RPM equals lower torque. But at the propeller, where it matters, the 2.43 to 1 reduction multiplies torque by the same ratio. The 912 actually delivers more torque to the propeller than the O-200. Another benefit here is the overload clutch fitted to most 912s, which protects against prop strikes, bird strikes and shock loads, often preventing expensive overhauls after such events. So the bottom line is, does the gearbox require additional maintenance? Yes, but from personal experience, the 912 is one of the cheapest engines to maintain and achieves its exceptional reliability despite the gearbox. Unlike most aircraft engines with wet sump systems storing oil in the crankcase pan, the 912 uses dry sump lubrication with oil stored in an external tank. It's a forced flow system. The engine-driven pump draws oil from the tank pickup through an oil cooler, then pushes it through a filter before pressure feeding into the oil galleries. Oil collecting at the crankcase bottom returns to the external tank via positive pressure created by piston blowby. No scavenge pump needed as crankcase pressure forces oil out. The external tank separates oil from air using a tangential inlet that creates cyclonic motion. Centrifugal force throws heavier oil outward to settle at the bottom while air escapes through a neck breather. This system requires a unique oil level checking procedure. After shutdown, oil slowly weeps from the galleries to the crankcase bottom. Checking the external tank the next day would show below minimum oil level because much oil remains in the engine. For accurate pre-flight oil checks, ensure the mags are off, then turn the propeller by hand. This moves the pistons, creating positive crankcase pressure that forces oil back to the external tank, just like it does with the engine running. This is called burping the system. After oil returns and only air is pushed out through the oil line, you'll hear an audible gurgle. Only then will the external tank dipstick show accurate oil level. The 912 runs on both avgas and mogas, that's automotive petrol, with the highest available octane recommended for mogas. However, when using avgas, oil change intervals increase to every 50 hours and spark plug replacement intervals increase from 400 hours to every 200 hours. This is because lead contaminates and degrades the semi-synthetic oil, leading to quicker breakdown of its lubrication properties. The 912 ULS uses dual carburetors, one per cylinder bank. You might wonder why add complexity and potential failure points, but there are good benefits. With a single carb serving 4 cylinders, perfect fuel-air mixture distribution is nearly impossible. Intake runners vary in length and shape due to packaging constraints, and the cylinder offset of boxer engines means some runners will naturally be shorter than others. This creates uneven fuel and air mixture between cylinders. Some run richer, others leaner, causing uneven combustion and higher CHT spreads. Dual carbs solve this by placing each carb closer to its cylinders, enabling shorter, more uniform runners. This delivers more even mixture distribution and efficient combustion. Each carb can be individually tuned, which is both a pro and a con, since out-of-sync carbs can cause rough running. Synchronization requires both mechanical cable adjustment and pneumatic balancing, which needs to be inspected every 100 hours. The 912 IS eliminates this with fuel injection. It's a high-pressure electronic port fuel injection system with dual electric pumps, 2 injectors per cylinder for redundancy, and fully automatic mixture with barometric altitude compensation. The carbureted ULS also lacks a mixture lever, achieving altitude compensation through its Bing 64 constant depression carburetors. These use a piston creating a variable venturi that opens with increased airflow. As altitude increases, reduced air density creates less depression or vacuum, causing the piston to settle lower, automatically reducing fuel flow to match the thinner air, maintaining optimal fuel-air ratios. The piston's diaphragm rubber requires replacement every 5 years. The 912 doesn't generally need carb heat when intake air is drawn from inside the cowling. Carb ice is less likely here as it draws in warmer intake air that generally shifts it out of carb ice conditions, as well as holding more water vapor before condensation. It's not fully carb ice proof, of course. This is quite a popular setup, but carb heat systems are installed by some airplane manufacturers, especially important when using NACA intake ducts drawing intake air from outside the cowling. It's not difficult to argue that the Rotax 912 remains king in the 100 horsepower aircraft engine market when considering the facts and not listening to your friend's uncle who may not be as knowledgeable on the Rotax engines as they claim. I hope this helped clarify the often misunderstood complexity of the 912 engine and why it remains statistically the most reliable engine in its class, despite or perhaps because of these features. So how long do you think it will be before the 100 horsepower 912 is dethroned? Let me know in the comments. Thanks for watching. See you in the next one.